COMSOL Multiphysics, Lecture 8, Part 1, Steady State Thermal Analysis of a heat sink. Open the part file. This is a heat sink model that I've drawn earlier. Save the file on desktop. And then now I will use lifelink mode to calculate this problem. So I'll add in the software here, and then I'll open COMSOL Multiphysics in a separate window and enable lifelink to connect the two programs. So the two softwares are connected using lifelink. The 3D model and a solid heat transfer problem. And there are two modes. The first one is steady state. The second is transient. I'll choose steady state. And I'll load the geometry from SolidWorks. And this is the one. So I finished with the first step. For the second step, material, I'll add material, and in the building material I'll choose aluminum 6063 and make sure that the material is connected or linked with the geometry. So I finished with the second step. For the third step, meshing, I'll give it a finer mesh. Build the mesh. Step 4. First of all, I can give it a initial temperature, which is really not important because in a steady state thermal problems, the system will reach a thermal equilibrium where temperature distribution is stabilized and the temperature shift is almost zero. So actually the initial temperature will not be important, but in this case it is designed here, so I'll give it 25 degrees C or 25 plus 273 degree K. And now for the loading, I'll give it a heat flux at the bottom surface, and it is here, overall heat transfer rate, and I'll give it 28 watts of heat source at the bottom. And now for the boundary conditions, I'll use heat flux again, and I'll enter a convection heat transfer coefficient of 10 watt meter square degree K, and also the ambient or environment temperature of 25 degrees. And I'll have to use all boundaries and choose all the surfaces except for the heating surface. Right, so I choose all the surfaces, and these are the surfaces that get in contact with the air, and the air is still air or stagnant air, and the coefficient of convection is 10 watt meter square K. So now this is the boundary condition, and this is the loading, the heat source of 28 watts. So now it is a steady state condition, so I don't have to give it a certain time to calculate. So I go ahead and compute, and I'll get the temperature result of the whole body, the temperature distribution of the heat sink. But the color here, I don't like the color, so I'll change from thermal light to rainbow light, and this is a kind of temperature distribution that I'm more comfortable with. You can change it to rainbow light, or you don't want to change to rainbow light, you can remain a thermal light. So I'll change to rainbow light. Okay, so this is the temperature distribution of the heat sink when the time goes to infinity and the system become a thermally equilibrium. And I'll get a point evaluation on this point and evaluate. And the number is 393.94. So it is about 100 degrees C at this part. So this is the temperature of the heat sink at the top point when the time goes to infinity and when the system becomes thermally equilibrium.